Okay, in this video, I'm going to talk about the rule of V's. Let me get my better microphone going here. I'm going to talk about the rule of V's and how we use that in geologic mapping. So just kind of to back up for a second and think about when we're looking at geologic contacts, we can break down geologic contacts into just three basic types. There's only three types of geologic contacts. And by geologic contact, we just mean a boundary that separates one rock body or package of rock bodies from another. So we can break these down into our three basic types: depositional contacts, intrusive contacts, so a plutonic intrusive body that intrudes into the earth, and structural contacts, so things like faults and shear zones. And what I want to emphasize here is that depositional contacts and structural contacts, they are generally planar features, or they're planes in space. Whereas intrusive contacts can sometimes be planar, but they can sometimes be irregular and non-planar. So it turns out that planar features, so primarily depositional contacts and structural contacts, they are going to have a characteristic map pattern. So homoclinal features are any type of contact or body of rock of uniform dip, whether the layers are horizontal or vertical or inclined. Yeah, so if you ever read in the literature someone talking about a homoclinal bed, what they are basically just saying, in other words, is they're talking about a planar feature. Okay, so again, we're talking about depositional contacts and structural contacts. Just to add a caveat to that, though, rarely do layers remain perfectly planar for great distances. They can be curved or slightly curved or corrugated, but many layers or features are nearly planar, and that's what we mostly care about. And so the maps of these types of layers, they're going to closely resemble the map patterns of those that are a true perfect plane. So the point of this video is to kind of help you visualize the way planar contacts intersect with topography on geologic maps. Okay, so just to begin thinking about this, just imagine, so I have this kind of this block model of a perfectly flat Earth. And in this perfectly flat Earth, we have a couple of layers that are to tilted to the east by 30 degrees. Okay, so they're striking north, south, and they're tilted 30 degrees to the east. Okay, so if the Earth were perfectly flat with no variation in topography, then this is what the map of of these layers would look like. It would be very simple. Okay, our contacts would be perfectly straight lines, and those straight lines would be perfectly parallel to the strike of of these layers. Okay, and in cross section, it would look like this plane here I'm illustrating. But that's not the case. The Earth's surface, except in a few rare places on Earth, the Earth's surface has topography, and even places that are seemingly flat have some amount of topography. Okay, so consider the pattern of a planar bed actually in map view and kind of in cross-sectional view or 3D view as it intersects with uneven topography. So in this case, we have a stream valley that is parallel to some elevation contours. Okay, so this is the map view. This is the 3D view of this scenario. Okay, so notice the map pattern of horizontal layers. The map pattern of horizontal layers are contacts between tan unit, purple unit, and blue unit. Okay, when the beds are horizontal, the map pattern perfectly follows the elevation contours in map view. Okay, and so this is what it would look like in um, in kind of 3D view. You can imagine that the contact between the tan and purple unit is a plane that connects across this eroded canyon. Okay, so that's a very simple case of horizontal beds interacting with uneven topography. But what do things look like when we have a planar feature that is actually tilted, and how that interacts with uneven topography? Okay, so here's the same river valley. The oblique view is a little bit different. Okay, in this case, we have planar features that are striking, again, they're striking north-south, but to they're tilted to the east about 45 degrees. Okay, so what you can see in the map view is that the tilted beds make this V-shaped pattern as they cross topography. Okay, so that's what we're talking about when we're talking about rule of V's. It makes this V-shaped pattern. So the contact lines, again, they do not follow the elevation contours. And in this case, they're cutting across them at acute angles, almost perpendicular angles. So it's very different than the case of horizontal layers. Okay, and again, we can imagine the contact between the purple unit and the tan unit is still a plane that actually connects across this eroded canyon, and all the other units too, for that matter, would also look like this. One cool thing is that we can actually we're not going to go into super detail into this in this lecture, but we can use the way that a planar feature intersects with the uneven surface on Earth to our advantage. The first most basic thing we can see is really just the general dip direction of the contact by simply noting the direction that the apex of this V is pointed. Okay, so the apex of the V as it crosses a valley, it's going to point in the direction of dip. So just qualitatively, I can look at this map and say, these beds are tilted to the east. Yeah, but we can actually get quantitative with this and actually determine the strike and dip of planar features just by getting the map pattern, how that interacts with elevation. Okay, so we can get strike by finding two locations along, here's our contact, two locations where the contact intersects the same elevation contour. Yeah, so that's these two red dots showing our contact intersecting the same elevation contour, 40 feet. If we just connect the lines between these, if we connect a line between these two, then that's actually the strike in map view. So we would take an azimuth of that. To get the dip, we would find more places where this contact crosses topography at different elevations. So if I put a dot here at the 30 and 30, okay, and draw another strike line, I've made a map of structure contours. And now, if we do this in several locations and make a structure contour map, then we can actually use trigonometry to determine the dipping. Okay, so we're able to determine the change in elevation from 40 to 30 and even lower over some horizontal distance. So then we can just use simple trigonometry to figure out the dip and calculate the dip angle from horizontal. Okay, so when we look at a geologic map, and if you ever go and look at published geologic maps, you'll see sometimes stuff that just looks like this. Okay, very complex, irregular patterns. And those are because the patterns of planar contacts are these complex patterns of planar contacts are really mainly due to irregularities in topography, or in some cases due to changes in thickness to a rock unit. But I can look at this map, even though it looks complicated, and because I use psychedelic colors here, I can tell that actually this is folded into an anticline, and that rocks on this side, okay, are tilted to the north based on the V of these contacts, and that south of this fold line, rocks are tilted to the southwest. So to the northeast up here, to the southwest up here. Okay, so this looks complicated, and you might scratch your head like, how am I ever going to get to the point where I would be able to make a geologic map that looks this complicated? And when you look at an area that has what we would say 100% exposure, it's very simple because we can just look at the aerial imagery and trace along contacts, and you can see that these contacts V across topography. Um, but in the case of the complicated looking map, what you kind of start to realize, and in a simple map, is that the rule of V's eventually becomes pretty intuitive, and you're able to make pretty complicated and accurate maps just by following the rule of V's and thinking in 3D space. Okay, so here's the map of that previous aerial image. Um, this is this is some some dipping planar beds on a geologic map of the Camargo syncline in Bolivia. And it looks complicated, but really it's just showing us that all these beds, and we can see from even the strike and dips, they are striking generally to the north-northeast and tilted on this side of this fold to the west. Okay, so the complex patterns of dipping planar beds, they eventually pose a little difficulty in visualizing and mapping in the field if you just kind of keep the following characteristics in mind. The contacts first, the contacts of horizontal layers, like flat lying strata in the Grand Canyon, those contacts are going to be perfectly parallel to and will mimic the topographic contours. Okay, and at the extreme opposite end of that, the contacts of vertical layers are going to form straight lines on topography, on maps, regardless of topography. Okay, and so any time we're kind of between these two extreme end members of horizontal kind of layer cake stratigraphy and perfectly vertical tilted 90-degree stratigraphy, the contacts are going to be tilted to some degree. And the contacts of dipping or tilted beds, they're going to form V-shaped patterns where they cross ridges or stream valleys. Okay, so I'm gonna illustrate this by looking at some stuff we're going to look at some stuff together on Google Earth. Okay, so we're going to look here in kind of the Grand Canyon area, Havasu. Okay, and in Google Earth, it's kind of cool. You can download KMZs of the topographic maps. I'm going to make this visible. Okay, so I can overlay it in space, and we can look at the aerial imagery and look at some contacts, draw them, and then see how they're going to look in comparison to the topographic map. Okay, so how they interact with elevation contours. Okay, so I can zoom in anywhere in this area and just to illustrate this point. Okay, you can kind of see this pinkish layer here. We're going to focus in on that. And I'm going to turn this map off for a second. I'm going to draw a contact on here. Draw a line. I'm going to draw a path here and kind of really make this very simple. Okay, but you can see in this area of like 100% exposure, it's so easy to follow the contact lines. Okay, so I'm going to draw along this contact semi-carefully. You can follow this kind of single ledge here. And then I'm going to turn um, the topo map back on. Let's make this, let's make it red so we'll be able to see it in thick. Okay, so there's our contact between some horizontal layers. Okay, so if I turn on the map here, we see again that in areas with horizontal stratigraphy or layer cake stratigraphy, the contact more or less follows the elevation contours. Okay, so it's mimicking the elevation contours. So it is in a way Ving, I guess you could say, but it's following the elevation contours that V across drainages as well. Okay, so that's an example where we have layer cake stratigraphy. Let's look at a place where we have more complex tilting of beds. Okay, so I don't know if I was recording the last bit. This might be a repeat of what I just showed, but we are looking at a place in Utah, the San Rafael Swell, where we have near 100% exposure. So there's no trees, and we can and not hardly any soil, so we can see the contacts almost 100%. So I'm going to zoom in here to these layers over here, this kind of purple band of cliffs, and I'm going to draw a contact along here. And then I'm going to turn on the topographic map, and we can look and see what this looks like. Okay, so if I turn on the topographic map, oops, I went off the map. If I turn on the topographic map, okay, I would see what that looks like. If I can continue the contact here, it doesn't matter. So I'm going to keep drawing this over here. Following the same kind of band of cliffs with that red to purple transition. And as it crosses this kind of canyon here, I'm going to try and follow it in there. And we can see what it looks like on the map. Okay, so a couple things to illustrate here. Okay, so notice as this contact line crosses a valley or the stream canyon, it cuts across the elevation contours and it V's in the apex of the V points in the direction of dip. So it's pointing to the east. Another thing to kind of point out here, too, kind of a rule here, is that contacts that are striking parallel to elevation contours are gonna generally follow elevation contours until we have a drainage that it crosses. Okay, so in this case, the contacts are actually slightly following the contours, although they are cutting across them at a slight acute angle. Here's another spot down here where I traced out some contacts here where you can see really very well these teeth-shaped contacts. Okay, so they're Ving every time it crosses one of these small little canyons that are cutting across the contacts. So if I turn the map on, is Google going to crash on me? There we go. We turn on the topographic map, we can see that this contact it doesn't express itself as a straight line. It's kind of this seesawing teeth-shaped contact that's Ving as it crosses topography. Okay, so in this case and the last case in the Grand Canyon, the two examples I'm showing you, these are depositional contacts. Okay, depositional contacts, again, a type of planar geologic contact, but structures can be planar as well. So I'm going to show you a spot near Las Vegas at Red Rocks Canyon, where we can see a fault surface that's planar. So fault surfaces, shear zones, those can be planar features as well. Okay, so this is the Red Rock Canyon National Monument area. So it's west of Vegas. Okay, and you can see this pretty spectacular feature here. These gray rocks that are sitting on top of these kind of golden or red colored rocks. And let me zoom in here. Okay, these kind of golden colored rocks, these are Mesozoic in age, and these gray rocks are Paleozoic. Okay, and you can see, I can just see right off the bat from the way these V across topography that the gray colored rocks are tilted to the west. Okay, and because these are older rocks that are, you can, if I turn this way, you can see the older rocks are on top of the younger rocks. That means that this is a fault. This is a thrust fault that places older rocks on top of younger rocks, Mesozoic rocks. Okay, so again, faults are planar features, and in this case, we can see the contact is pretty spectacular here. This transition between gray colored rocks and golden colored rocks. And let me turn on the map again for a quick second, the topographic map, so I can see where I want to trace things. Okay, so we're gonna trace through here and see what this contact looks like in map view. Okay, so I'm just gonna draw along here, following this contact between gray colored rocks and golden colored rocks. So what this video should illustrate too is how valuable of a tool Google Earth can be, in part because it's so simple to use. It's very user friendly, and there's a lot of KMZ files of geologic maps that are just ready to go to drop into Google Earth. So you can do stuff like this a lot of times when you're scratching your head over what would the orientation of my map contact, or what should my map contact look like when I'm drawing it on a map. Okay, so when I turn on the map here, okay, so just looking straight down again, I'm looking at this feature, looking to the west right now. I can see, I can already tell just by the orientation of the structure, it's going to be pretty shallowly tilted to the west. So it's going to have a low dip magnitude. So if I turn the map on, what that's going to look like once the map pops up here is that in some cases, the it's going to have these kind of really gentle V's as it crosses a valley right here. Okay, so as it crosses this kind of big valley and topographic low, it curves way back here into the topography. And another important point about rule of V's is that actually when contacts cross ridges, they also are expressed as a V-shaped map pattern, except that the V points in the opposite direction as when the contact crosses the drainage. So again, looking down straight on the topography, okay, this is an irregularly curved line. This is how geologic contacts look in real life. The only time, again, the only time you're going to have vertical contacts is when the, or sorry, excuse me, the only time you're going to have very perfectly straight contact lines is either there's no topography or the stratigraphy or the planar feature is a vertical feature. Okay, so things like strike slip faults, those are typically vertical features. And so those often express themselves as perfectly straight lines on a map. Okay, so for our next, so these are cases where you can see the stratigraphy 100%. There's hardly any trees, or the color difference between geologic units is so drastic that it's just easy to tell where the contact should go. Okay, so in the next example, I'm going to take you near Pocatello, the Bear Camp Gulch Quadrangle. It's on the backside of Pebble Creek. I'm going to show you kind of what how you operate when you can't see where the contacts go. Okay, so just keeping the rule of V's in mind, we can estimate how the contact should look in space. Okay, so we are over in the Pocatello area. Here's Pocatello, here's Ingham, Pebble Creek Ski Resort is here. This is the Portneuf Range. And back here is a place called the Bear Camp Gulch. So I'm going to turn on the topographic map for a second. And once it pops up, we'll zoom in. Okay, and so what you can see from the topographic map actually is places where there's lots of green on these USGS or Forest Service topographic maps mean there's a lot of vegetation. Okay, so again, in the previous examples I was showing you, those are areas where there's like 100% exposure. There's no trees in the way. There's no soil development in the way. There's no sagebrush in the way. You can see where the contacts go. Okay, so what often happens in real life, okay, is that you end up in a situation like this. Okay, you can find maybe a slope where you can find your contact. Okay, so this kind of gray, we're going to say this gray unit is our contact between two different geologic units. And if you can see it curves across the landscape. Okay, and as we follow it across this drainage, it would V down this way. But then we get over here and we have this hill, okay, you can see that is heavily forested and there's lots of soil development back here. And so we have to estimate where the contact should be located and draw it in on our map. Okay, so I'm going to do that. I'm going to use my rule of V's. First, I'm going to draw this while the map is off. Okay, I know that it must go down here somewhere where I can actually see it. When I turn the map on, I have to turn this off for a second. When I turn the map on, give it a second, it's thinking. Okay, I know just thinking in rule of V's in kind of 3D space, it's the contact's probably going to come up somewhere like this. And as it does, it's probably going to have some slight variation to it, going to even interact with these smaller dips in the drainage like this. So this is how I would approach this problem. Okay. And the utility of this is I can be standing over here, be certain of where the contact is on this mountain. Okay. Maybe I can then draw or project where the contact line where I think it should go, thinking in rule of V's. And then as I walk down this hill, I can walk around in my map and see what I can find in the colluvium or small outcrops that might be in the trees to actually find a spot. So say, for example, I find it here. Well, then my prediction was correct. It should follow just how I drew it. Okay. Or maybe sometimes you might find that you're able to find a contact. Forget that line. Okay. Let's say, for example, you are able to find a contact here and you walk around with all of your best intentions and you can't find one until you're back in here again. Okay. And then you're able to find another one here. Okay. So I know with certainty I have these three spots where I can be sure of where my contact is located. So then I'm using rule of V's to make a prediction about where the contact should go and how it should connect to the places where I know the contact exists for certain. Okay, and so as you're out in the field and mapping, you're taking strike and dips at the places where you can find the contact because it's telling you the direction of dip. You're building hypotheses as you're walking around in the field. It tells you also what the direction that the strata is going to V across topography. So if I found this contact first over here, then I would expect that, and if my measurements tell me it's dipping to the west, then I know that I'm not going to find the contact over here unless something is messed up, right? I know that I'm going to have to go back into this valley here to find that contact. Okay. And again, once I find it here, I know because of rule of V's, it's not going to go shooting off straight up here. Okay. It's going to wrap back around the front side of this hill. Okay. So again, when I look down at this contact and I see that it is aimed or tilted this way, it's Ving that way. So it's pointing to the west. It tells me contacts on this side are Ving to the west. Okay. And where I showed you here on this side, contacts are kind of being the way they cross topography. They're being to the east. That tells me actually there's a fold here now too, because I can see contacts on this side, V to the west, contacts on this side, V to the east. The only way to do that is to make a fold, a syncline, where my layers are folded in towards each other. Okay, so that is using Google Earth to kind of illustrate those points. And so back to this PowerPoint here to kind of to summarize, sharing the right screen. Let me double check. Okay, to summarize, okay, the contact patterns of planar features. So when layers are flat, layer cake stratigraphy, like in the Grand Canyon, layers that are horizontal or close to horizontal, they're going to show contact patterns that mimic the topographic contours. They're easy to draw because basically you just follow the, the contours. Contact patterns of something that's a vertical bed. So here's showing the end member extreme to being horizontal as being vertical. Okay, so something like a dike or layers that were once horizontal have been tilted to vertical, they are going to trace out as a straight line as they cross topography. Okay, so there's no deflection of this contact as it crosses this drainage here. So no V to our contact line. Okay, so we can kind of summarize or sum up our rule of V's. Okay, the rule of V's are, or it is the map patterns of contacts that are tilted. Okay, they'll generally have the shape of a V where that contact crosses a valley. So here's our valley. You can see the contact in 3D, what that looks like. If a V-shaped pattern occurs in a stream valley, the apex of that V, it generally points in the direction that the layers are tilted, okay, or what we would call dip direction, regardless of whether the layer dips upstream, okay, like in this case, it's dipping upstream. It would V across the topography, cuts across the contours, or whether it's Ving downstream. In either case, the apex of the V points in the direction that the layers are tilted. Okay, so that's kind of in sum what our rule of V's is. How exaggerated the V-shaped pattern is, it depends on two things. Okay, so in this case, it's kind of, in this case, it's barely coming off of the contour lines. It depends on how rugged the topography is, or how extreme the tilt is. So in this case, again, a horizontal bed, it still shows a V-shaped pattern as it crosses a stream canyon, but it mimics the contour lines. The more tilted something is, the more it's going to V across topography. Okay. Or sorry, the more tilted something is, the less it's going to V as it crosses a canyon, to the point of where it's vertical, it's just a straight line. Okay, so there are just a couple special cases where the bed dips, where the rule of V's might fool you. I've rarely ran into this occurring in my own personal experiences, but where the bed dips downstream at an angle that's less than the slope of the stream. Okay, that's a case where actually the rule of V's actually won't point in the direction of dip. This is pretty rare to see. So it's important to be kind of tracking your strike and dip in the field and remembering that. That's important. Okay, so this concludes this video. Now you are capable of thinking in 3 dimensions and following the rule of ease.